All right, let's talk about a really cool algorithmic trick. Imagine you've got this huge data set, right? And you're getting slammed with thousands and thousands of questions about it, and you have to answer them fast. The big problem? You can't just start from zero for every single question. So what do? Well, there's this super clever technique called Mohs algorithm, and today we're going to break down exactly how it works.
So let's really set the scene here. You're in a coding competition, the clock is ticking, you get this problem, a massive array of numbers, and just a ton of queries. And each query is something like, hey, between index 100 and index 5000, how many distinct numbers are there? Now, answering just one of those, no problem. You can do that. But answering thousands of them, your program is just going to time out, it's going to grind to a halt. That's the exact problem. That's the wall we're trying to get past.
This leads us right into the big, obvious problem with the straightforward approach, the range query problem itself.
The naive approach, the one we'd all think of first, is to just, well, rescan the array for every single query. You get a query from range A to B, you loop from A to B. Simple, right? But it's also incredibly inefficient. I mean, let's be real. If you have 1 million elements and 1 million queries, you could be looking at something like 1 trillion operations. That's not just slow, it's never going to finish. So yeah, that idea, we got to throw it right out the window.
Okay, so what's the alternative? This is where it gets really, really cool. The solution isn't some super complicated new data structure you have to learn. It's actually a surprisingly simple, almost counterintuitive trick. The whole idea boils down to one question. What if we just answer the queries in a different order?
And that brings us to Mohs algorithm itself. By definition, it's an offline query processing technique. Now that word offline is the key to the whole thing. It's super, super important. It means we have to know all of the queries we're ever going to be asked right from the start. Why? Because the entire magic trick is based on reordering them to be as efficient as possible. It's a trade-off, right? You lose the ability to answer questions as they come in, but what you gain is a massive speed-up.
So yeah, this is the secret sauce. The whole thing is about answering queries in a smarter order, not the order they were given to us. You can think of it like being a delivery driver. You wouldn't just drive to addresses in the random order you got them, right? You'd jump all over the city. No, you'd plan a smart route to minimize your driving time. That's exactly what Mohs algorithm does. It sorts the queries so we can get from one answer to the next with just a tiny little adjustment, instead of starting over every time.
Okay, so how does it actually do that? How do we find that smarter order? Well, this is where the mechanics come in, using two key ideas: blocks and sliding windows. Let's imagine our array isn't just a list of numbers, but a long street of houses. Each query is asking us a question about a specific group of houses on that street. Mohs algorithm figures out the most efficient way to walk down that street and answer every question.
It really boils down to 3 main steps. First, we take our long street, our array, and we divide it into blocks of a specific size, roughly the square root of n. Think of these like neighborhoods. Step 2, and this is the magic part, we sort all our queries. We don't sort them by their start or end point, but by which block their starting point is in. This clumps all the nearby queries together. And finally, step 3, we use a sliding window to answer these newly sorted queries one after another.
Now, this quote really gets to the heart of it. We keep this sliding window over our data. What does that mean? It means we have a current range we're looking at. And to get to the next query's range, we don't just jump there, we just nudge the window. We extend the right side one step or shrink the left side one step. We literally just slide it over one house at a time, and with each tiny move, we update our running count. It's so much more efficient than starting from scratch.
Okay, but there is one huge requirement. A deal breaker, really. This whole sliding window thing, it only works if you can add or remove a single element and update your answer in constant time, or O of 1. Think about it. If every time we slide our window one step, we have to do a bunch of complicated work to update the answer, we haven't saved any time. The update has to be super, super fast, like adding a number to a frequency map or removing one. If it's not O of 1, Mohs algorithm is just not the right tool for the job.
So, why do we go through all this trouble? The reordering, the blocks, the sliding window. What's the point? Well, the point is the performance payoff. And trust me, it is massive.
I mean, just look at this comparison. The total pointer movement, which is basically the total work we're doing, is night and day. With the naive approach, you're looking at something that could be OQ times n. That's the thing that times out. But with Mohs algorithm, it's O n plus q times the square root of n. That might look a little complicated, but the bottom line is, it's so much faster.
This is literally the difference between time limit exceeded and accepted.
So let's talk about that time complexity. O of n plus q times the square root of n. You see this everywhere with Mohs, but where does that square root come from? It's actually really clever. It's all about balancing the work. By making the block size square root of n, we make sure that the two main costs, the left pointer jumping between blocks and the right pointer sweeping across within blocks, are perfectly balanced. Neither one can get too big and dominate the runtime. It's this beautiful sweet spot that makes the whole thing work so well.
Okay, so we've covered the how and the why. Now let's get super practical. Let's build a playbook for when you should actually use Mohs algorithm. When you see a problem in an interview or a competition, what are the signs that scream, hey, use Mohs here?
Here's your checklist. These are the green lights. First, the array has to be static. No updates to the values between queries. Second, you have to know all the queries beforehand. Remember, it's an offline algorithm. Third, and this is the big one, the problem has to support those super fast O of 1 add and remove operations. And finally, it's most useful when you have a large number of queries. If you check all these boxes, Mohs is probably a fantastic choice.
And just as important, here are the common pitfalls, the red flags to watch out for. First, don't even try to use it for online queries, where you get them one at a time. It just won't work. Also, a pro tip, if the numbers in your array are huge, you might need to use value compression first. And of course, don't mess with the block size. It really needs to be around the square root of n for that optimal balance. And I'll say it again, if you don't have those O of 1 updates, just find another way.
So you might be thinking, how does this compare to something like a segment tree? It's a great question. The best way to think about it is there are different tools for different jobs. A segment tree is amazing. It can handle updates to the array, it works online, it's like a power tool. But Mohs algorithm is like a specialized hand tool. It can't handle updates, and it has to be offline. But for the specific job it's designed for, like complex frequency queries on a static array, it can be way simpler and sometimes even faster to implement.
And that really leaves us with the final thought. The biggest lesson from Mohs algorithm isn't just about square root decomposition, is that sometimes the most powerful optimization isn't a fancier data structure, it's just looking at the problem from a different angle. It makes you wonder, right? What other hard problems out there only seem hard and could get a whole lot easier if we just stopped and thought about changing the order of things? It's definitely something to think about.